Today we want to look at the first order differential equations involving the use of the integrating factor. So these types of equations occur when the equation is of the form dy dx plus py is equal to q. And please note that p and q are both functions of x only. So the method of solution involves the use of the integrating factor u, which is equal to e raised to the integral of p dx. So let's look at how we solve these equations. So we have dy dx plus py is equal to q. And let's look at the integrating factor now. So let's label this equation 1. So u is equal to e raised to the integral of p dx. Let's take the ln of that. So you're going to get ln of u is equal to ln of e raised to the integral of p dx. And the ln of the exponential is just whatever is the function up here. So it's the integral of p dx is equal to ln of u. And let's differentiate implicitly. So you're going to get 1 over u du dx. And the derivative of the integral is just the function itself, so as equal to p. So du dx is going to be equal to pu. Alright. So we go back to our first equation, which is dy dx plus py is equal to q. And let's multiply equation 1 by our integrating factor u. So what do we get? We're going to get that it's u dy dx plus pu is equal to qu. Pu by y, sorry. So this equation 2. But pu is equal to du dx. So u dy dx, by making a substitution now, becomes y du dx is equal to qu. Now, let's look at something very quickly here. Let's look at the derivative ddx of uy. Alright, and we're going to differentiate this implicitly. So remember, we differentiate y, leaving u alone, so that's u dy dx plus. And we differentiate u, leaving y alone, so that's y du dx. So we're going to substitute now ddx of uy for this u dy dx plus y du dx. So what we get now is that ddx of uy is equal to qu. And uy is going to be the integral of qu with respect to x. And this is how we go ahead. This is how we really find the solution to differential equation, okay, using the integrating factor. And now the solution can then be easily obtained. Alright. However, when we do an example, we don't need to show all of this working. What we could possibly do is to move from this line directly to this line. What I have done is just shown you the proof of it, so you actually can understand what is happening. But in doing a solution, you don't need to show all of this. Okay. So let us now look at an example. Okay. So let's say we have cos of x dy dx plus y sin x is equal to 1. Now, first of all, we have to ensure that our equation is of the form dy dx plus py is equal to q. So we are going to divide by cos x, and we will get dy dx plus y tan x is equal to sec x. It was equation 1. And this is of the form dy dx plus py is equal to q, where p is equal to tan x, is a function of x only, and q, which is equal to sec x, is also a function of x only. So what we're going to use now is we're going to find what the integrating factor is. So u is equal to the e times the integral, or e raised to the integral of p dx. And this is equal to e the integral of tan x dx. So let's do this integral on each side here. So we have the integral of tan x dx, and this is really the integral of sin x over cos x. So we let t equal to cos x. So dt dx is equal to minus sin x. So therefore, the integral of tan x dx is equal to the integral of sin x over t by dt over minus sin x. This cancels off. So the integral of 1 over t, or negative 1 over t dt, which is equal to minus ln of t plus c, or minus ln of t. We don't need the c at this point, which is equal to minus the ln of cos x. So our integrating factor u is equal to e to the minus ln of cos x dx, and this is equal to e to the ln of 1 on cos x, which is equal to, so the integrating factor u is 1 over cos x. So now we go to multiply equation 1 by u. Alright, so what we get is 1 over cos x, or just remember 1 over cos x is equal to sec x, so let's use that instead. So it's sec x by dy dx plus y tan x sec x is equal to sec squared x. And let's label this equation 2. So as I was telling you before, as illustrated, we can go directly now from what we just did, multiplying the equation by u, directly to the ddx of uy is equal to q. So now d dx of uy, so this is y sec x, right, is equal to qu, and that is sec squared x dx, sec squared x. So integrating both sides, we're going to get y sec x is equal to the integral of sec squared x dx, which is equal to tan x plus c. So y is going to be equal to tan x on sec x plus c on sec x. And when we simplify, this is just going to be sin x plus c cos x. And again, c is a constant of integration, and since we have our constant c in the equation, this is what we call our general solution. If we were given conditions, we could substitute for those conditions, let's say for x and y, and we would get a particular solution.